Alright, so problem 26 is going to demonstrate the shell theorem and density stuff. Alright, so first off, we need to find, well, we have a planet Earth, just a planet. Uniform density, so that's why we can use the shell theorem in the first place. And we need to find, well, first off, if you're on the surface, the force of gravity you experience is F, we'll say Fr, because r being the radius. So they want to know where out here, somewhere, is the force, do you experience half Fr? That's for part A. And for part B, where inside do you experience half Fr? So we're going to, that's if you had dug a tunnel deep into the earth. So let's do that. Alright, so first off, what is Fr? Well, Fr at the surface is big G times your mass times the mass of the planet over the radius of the planet squared. Alright, so if we solve this for the radius of the planet, let's rearrange. You get the square root of radius, because we want to figure out how far, like a new distance, so maybe in terms of radius. So it becomes G M P over F R. So that's the radius of the planet in terms of the force. Okay, so for part A, excuse me, we want to know how far when you have half the force. So we're going to just stick in half the force here. G M P over half the force. And you should be able to see that this is you could pull out a square root of, well, you could actually rewrite this, so do 2 over 2, these cancel, so the 2's on the top here, so you could pull out a square root of 2. See what I did there? I took half of FR, but then half on the bottom of a fraction. You can just take the reciprocal and make that 2, and that 2 is still in the square root, so I pull the square root of 2 out. So essentially this is these two are the same, so this is really root 2 times the radius of the planet. So that's how far out you'd be from the center. Now it wants to know the altitude. So altitude, that's like just the distance above the surface. So what's this distance? Is the total distance out from the center minus the radius of the planet. So that's going to be root 2 RP, this is the total distance from the center, minus RP, so it's just going to be RP times root 2 minus 1, which we could make a decimal if we wanted, but I'll just leave it like that. Oh, excuse me. It's 6:30 in the morning. Alright, part B is asking where, if you dig a tunnel into the earth, where is the force half Fr? How deep? First thing, we need to take advantage of the fact that it's uniform density. So density inside equals density at the surface. So density is mass divided by volume. So this becomes mass inside over 4/3, this is the volume of a sphere, 4/3 pi r inside cubed equals mass of the planet, because at the surface you get the mass of the entire planet, over 4/3 pi r planet cubed. 4/3 pi cancel. And so this is essentially the mass at any radius inside. Alright, and so the inside force inside, we can use the shell theorem, is only going to include, well, first it's g times your mass, but it's only going to include the mass of the planet that's inside of you. That's like, so if you're like here, this deep down, and you make a shell, the force you're going to feel is only from this mass inside this dashed circle. None of this mass out here in this outside shell affects you. So this is over the inside radius squared. Alright. Well, we can solve this for m mass inside. Just bring the r inside cubed up here, and then replace that over here. So this becomes g m mass of the planet r in cubed over r in squared rp cubed. So mp rn cubed over rp cubed was this, and then this stuff is from over here. So these cancel with two of these, which becomes g m p r in over rp cubed. Now we want the situation where I'm going to do this up here. We want the situation where the force inside is half the force at the surface. So force inside is this, so that's going to be, we're just going to copy this result that we just got here, p r in over rp cubed equals 1/2, and fr, we're just going to use this original value way over here, g m p over rp squared. So things cancel. g m p, g m p, these two rp's, two of these. So we'll just bring this third rp up, and we get r in, because that's all that's left over here, equals 1/2 r of the planet. So you basically have to go halfway down, halfway into the earth. Alright, so that was a good use of the shell theorem to ignore the outside mass for here. A good use of uniform density to relate masses and radius at any point inside the planet. And a good use of altitude, being the distance from the center minus the radius of the planet. And that's pretty much it. Alright, and we'll go on to problem 38 next.